Good morning, good afternoon, good evening, good night, whenever it is you're looking at this, welcome. I'm going to be working through yet another one of the lessons for the second half of Calculus BC. In today's lesson, we're going to extend the work that we did in the previous one, focused on Taylor and Maclaurin polynomials, and we're going to start to look at this new idea called Power Series that's going to sound like it's something new, but is really just a different way of looking at that Taylor and Maclaurin polynomial work that we did before. So it's just going to be kind of a small adjustment. We'll change some notation, but we'll be able to develop some really powerful tools. Truthfully, you may not hear it in my voice, but this is actually probably my favorite lesson of the entire course. This is one of those topics that just kind of excites me. Like all morning I've been excited about possibly getting the chance to do all of these problems. I just like doing the problems, honestly. Many people have told me in the past that I probably shouldn't be that excited about it because it's just kind of computational. There's not really a lot of application, and typically I really like the applications and the potential for a Cuddles movie. But I just like doing this. This is just kind of figuring out how to do it, and you're exploiting tricks, and there's 3 different ways to do every problem. I like that stuff. I like the algebra myself. And this is going to be something that finds a way to get out of the massive differentiation tasks we've done before. In addition, by the very end of this lesson, we'll actually be able to do some really powerful stuff. We'll be able to anti-differentiate some functions that we couldn't anti-differentiate before and get really good pictures of what those antiderivatives would look like, even though they're actually impossible mathematically for us to anti-differentiate. So there's going to be some really cool outcomes that come here. The only thing I will say is before we begin, it's really important to note that you do have to have kind of mastered the construction of a Taylor or a Maclaurin polynomial from yesterday or from the previous lesson, because if you don't, we're going to jump in at the very beginning here and you're going to be like, wait, where did that come from? How could I get that? Where is that at? I'm going to try to move through the topic very quickly. Or I'm going to try to get into the topic pretty deeply, pretty quickly. So my recommendation to you is that you make sure you've really mastered that one before you attempt this one. Now, having said that, a couple things to point out. First and foremost, if you're someone that watches the hats I wear, I'm not wearing my Vikings cap. I don't actually have a clean Franklin one to wear, otherwise I'd be wearing that every single lesson. But having said that, I'm wearing a Timberwolves cap simply because, I'll just admit it right now, it's the first time I ever bought a hat simply because I liked what it looked like. Obviously, I've worn some different ones out there that are just kind of cool or interesting, but I don't actually root for this team, but I just really like the hat and the colors. And then second, when I'm wearing my shirt, I'm wearing my Dear Evan Hansen authentic polo. So this is modeled after the polo that Evan Hansen wears in the play Dear Evan Hansen. So because I was wearing blue, I didn't want to wear black, so the black would conflict with the navy. So here's where we are. You totally needed that information, but I know there are people out there paying attention to the attire that I'm wearing here because I'm not wearing the shirt and tie I normally would. Having said all that, though, thank you for being here to watch. Hopefully I'm going to get you some really good information, some powerful techniques, and you'll be able to walk out of this comfortable constructing, really, Taylor and Maclaurin polynomials, but in the guise of a power series. Something that's actually, as the name might suggest, pretty powerful. So let's get in and let's get started. So as we jump in here for the first time, let me point out that it opens here with just kind of a statement. You might notice patterns with some Taylor polynomials. And the answer is you probably did. In fact, we talked a little bit about it yesterday, the idea that we could theoretically predict what more terms would look like based on just seeing kind of the pattern of where things were going. We were able to develop a little bit of that. It's kind of a preview of today's lesson. Having said that, what I've done so far is I've written out the 3 functions that form, I want to say, almost the building blocks of all the other functions we're going to look at. These 3 share a specific property, a special property. It's not a property I can discuss just yet. We need one more lecture past this point. But just so you're aware, that property kind of brings these 3 together, makes them kind of special and unique. They also match the ones that I used to demonstrate the first, kind of the graphical or visual intuition when I opened up Taylor and Maclaurin polynomials, the previous lesson. So keep that in mind. The goal would be that you've already computed these, either in the lesson, which I know we did sine of x, or possibly on your own in the problem set. If not, if you don't trust that those are the Taylor polynomials or those are the correct patterns, please do go derive each expression yourself, use differentiation and develop out what all the coefficients will be and then put them with the appropriate terms. But right now, we're going to begin from the position that you already know what those 3 Maclaurin polynomials are, or that you can see what's happening. The reason for that is today's less about that massive differentiation process that we used before than it is about exploiting the patterns and the ability to represent these same polynomials in a slightly different form. So where I want to begin first is I want to point out that as we look at these three polynomials, or these three polynomials that seem to be getting bigger and bigger, it's like we're almost like we're ready to add more terms to each of these polynomials. I want to point out that you can probably see what the pattern is for each of these. So let's first just begin by actually writing in the general term for each one. And you know what, I'll put this in pink, I think. Yeah, we'll do that. So if we want to write the general term for the first one, actually that might be the hardest of the three. Let me start with the last one. I think the last one's actually pretty clean. So look at those denominators, 2 factorial, 3 factorial, 4 factorial. Notice those powers are 0, 1, 2, 3, 4. It looks like it's pretty clean. It looks to me like this one's general term would be 1 over n factorial times x to the n power. So it looks like that's describing how you would generate any particular degreed term for this particular polynomial. Of course, though, it wouldn't stop at n. It could go on forever. And if we wanted to be exactly equal to e to the x, we would need it to go on forever. Technically, this statement and this statement is false right now until we add that extra piece. So there's our first one. We found our general term. Some people, by the way, might write it as x to the n over n factorial. I have no opposition to that. I just prefer to write the coefficient style. I'm a coefficient guy myself. Now let's look at cosine and sine, though. A little bit different here. Cosine is 1 x squared, x to the fourth, x to the sixth. And notice that the signs are alternating also. Positive, negative, positive, negative, positive, negative. So it's following that pattern. So there are a couple things I can put in here first. Initially, I'm going to put negative 1 to the n, thinking that, of course, since we typically begin at n equals 0, like there's that term where you just have the original function. If I plug in 0, I'll get a positive first, so that looks good. For the powers, we have at 0, the power is 0, at 1 it's 2, at 2 it's 4, at 3 it's 6. My thought is, this looks like x to the 2n power. And then down below in the denominator, that value is just the same as the power. So that should be just 2n factorial. And then, of course, just like before, we need to complete this thing by adding that it would go on forever so that way we can say it's literally equal to cosine of x. Last but not least, we have sine. Well, I noticed that sine also has that alternating pattern. It has a power that's going 1, 3, 5, 7. So we need all the odd numbers. I happen to know that you can generate the odd numbers by adding 1 or subtracting 1 to all the even numbers. In this case, since we're going to probably start at n equals 0, I'll pick 2n plus 1. So we begin at 1, then 3, then 5. And then just like with cosine, the denominator, underneath that awful looking fraction bar I just drew, that denominator is going to be 2n plus 1 as well, because the factorials down there match all the powers for each individual term, or each respective term. So having said that, that accomplishes what we wanted. We now have a full polynomial. We have 3 correct statements. Now having said that, you can notice the patterns, and since these are 3 expressions, kind of 3 patterns that you are going to need to know, you're going to need to be able to recall them. Time-wise, it's probably not going to be enough time in the future for you to be able to differentiate 7 times or whatever to develop the pattern. Since you need to know these, it's worthwhile to take just a second to describe the patterns themselves. So in this case, the first thing I want to note is with looking at cosine, you have all the even powers. Sine, on the other hand, you have all the odd powers. And then e to the x, you just plain old have all the powers. All the powers. It's like you're Superman or Shazam or any of them that just have every single power in the world, and then I'm immediately disinterested in what's happening. So there's that first part. Excuse me. Turn on the air. My own fault. So from here, cosine, in addition to cosine being even, it's also alternating. Just like sine is odd and alternating. And then e to the x is all and positive. So there's no negative signs, no negative coefficients in that particular one. So having said that, just as kind of a note, these are things that you will need to know. So let me write that in there as well. These are need to know. Or this isn't one of those on a need to know basis. No, you need to know these 3, like They are important. They're going to show up constantly, and the sooner you kind of get those patterns in your mind, the better. So use that red writing if you need to. But instead, before I go forward, what I want to point out is that although we've been using the word polynomial to describe these things, we really don't have to. I mean, think about this. We're adding up, yeah, the signs are sometimes negative, but we're adding up a bunch of terms that have a set pattern, and we're adding up an infinite number of those. Doesn't that seem like the same thing as a series? The answer to that question is not rhetorical, is of course yes. It does look like these would be just the same thing as a series. And in fact, we could easily transform them into a series. So, oops, that's terrible looking sigma. Guess not so easily. For cosine, we could run from n equals 0 to infinity, and then inside we'd have that general term. In fact, that's not going to be a surprise. The whole general term is valuable because it allows us to generate more terms for this particular thing. So this expression would in fact give us cosine. The next one, we'd do the exact same thing that we just did. Take the sum, and then we'd just plug in the general term, and we would have exactly what you'd want. An expression that generates a series, even a series that generates sine. It would, every time you add terms, it gets more and more of sine of x taken care of. And then finally, for e to the x, the one that kind of looks like an outlier here because it's not alternating, you'd have your 1 over, I'll just write it this way since I talked about both notations, get x to the n over n factorial. So that would generate all of the function e to the x. And it would slowly converge more and more of it, just like yesterday where it kind of stitched. It'd be doing that same thing for each of these. So these series are the same thing basically as those Taylor and Maclaurin polynomials. In fact, that's the biggest thing I'd like you to take away from this first page as we've just started kind of investigating this idea. Taylor and Maclaurin polynomials, sorry, I didn't say that correctly. Taylor and Maclaurin polynomials. Taylor and Maclaurin polynomials are basically the same thing as some sort of infinite series. The only difference here with these infinite series from the work we've done in the past is that our infinite series is not actually just a numeric sum. These are actually functions of x, which makes them not technically infinite series, but a specific type of infinite series. Can you guess what the name is for those infinite series? Yeah, it's the title of the lesson. These are called power series. And so as it says on the second page, it says at the very top, Taylor and Maclaurin polynomials are just series that happen to be a function of x. And now that phrasing happen to be a function of x makes it sound kind of like coincidental or serendipitous. That's just what I'm trying to describe. They're series, infinite series, that are a function of x. So x is changing, meaning you can plug values into these series and change what actually happens. And in fact, the next lesson after this one is all about what values can you plug in and have that series actually converge. So there's some cool stuff still on the runway, on the horizon. There we go, on the horizons for us. So take a look at that definition. So a power series with variable x doesn't have to be x. In fact, later on in this lesson, I may actually use t at one point. So hopefully you're okay with a caffeinated beverage so that I can use t. So from here, it says a power series with variable x is an infinite series of the form right there or right there. And what I'd want you to notice as you look at those is they look just like a Taylor polynomial and a Maclaurin polynomial. In fact, I'll go so far as to point out that this first one looks like a general Taylor centered at C. I should probably write center C. That just looks pretty easy to notice. And this next one looks like a Maclaurin, which of course we know at this point that Maclaurins offer a center of 0 specifically. Now I will say that for the rest of this lesson, I think we focus mostly on Maclaurin series. Maclaurin series, there it is. I gotta get it in my head so I say it with the accent every time. So we're gonna focus mostly on Maclaurin series. But having said that, just know that Taylors are possible too. Just for simplicity and space and everything, we focus mostly on Maclaurin series. And in fact, you'll start to notice that I probably say Maclaurin series about as frequently as I say Maclaurin polynomial, just because series and polynomials in these cases are basically interchangeable with one another. They're describing the same thing, they're constructed the same way. It's just by allowing us to think about them as series or some sort of polynomial, there are different advantages to each one. So having said that, a couple things that I do want to point out is obviously something that's here is, let's make sure I get a good color here, is that inside these expressions, actually why would I put that down there? Inside the summation, in the part that's called the summand, you have the general term. Now we tend to think of that general term as the rule, and that's not a bad way to think about it either. It's like the formula, the structure we use to generate more and more terms of this. But just keep in mind that's the general term, and also that we have the general term right here in our series. So I do want to point out, just to make sure that you're aware and noting it, that the way this is written is actually quite important. If we want this to be an infinite series, and notice both of these power series are in fact infinite, that is the implication, then we need to make sure that we add all those infinite number of terms that we don't necessarily write out because of the impracticality of writing infinite number of terms. Make sure it ends with a plus dot dot dot. I use the convention because so frequently we were asked for it to write dot dot dots, then the general term, and then dot dot dots again. It's up to you if you want to include that, just to look at the instructions for the particular problem, but it's nice to have them there. Now, having said that, since we've been talking about polynomials, there is one little caveat we could throw in here. If you want to talk about specifically a certain degreed Taylor polynomial or Maclaurin polynomial, let's say you want a degree M, a master's degree. Sorry. Like, I did go to college and get a degree, but the whole time I just really wished I could have gotten a radian. It's a nice math version of a degree joke. So anyway, if you want to talk about a specific degreed Taylor polynomial, then you would, of course, as we talked about yesterday, you could call it P sub m of x. And then the way you would write that, or generate it, assuming it's centered at C, is in your summation, instead of going all the way up to infinity, which would imply an infinite number of terms, you'd go all the way up to m, because that would be your degree. And then you generate the terms of it the exact same way you'd expect. In this case, technically I guess I shouldn't say that. Well, I'll say it because I think you know already what's going on. You'd be able to generate it looking something like this. So again, I'm probably jumping a few steps there as well, but at the same time, there we are. So that would be our nth degree Taylor polynomial, and then specifically in this case for f of x, and specifically centered at C. Yeah, it's a lot to write. I think that was probably why I shortened it a little bit and cut it a little bit of a corner before. But in any event, there it is. So it's also possible for us to use a power series or represent a actual degreed Taylor polynomial as a finite series. So infinite series are power series. A polynomial would be of a particular degree would be a finite series. So there is kind of the definition. Now, of course, our goal here will be to work with these things and to try to exploit them and manipulate them in order to save us some time from what we had to do yesterday. So grindily, I don't know if that's a word, but like grinding through it slowly, one differentiation at a time. But before we get there, let's just practice getting comfortable generating these things. So right here, as our first little example, and try it together, I'd like us to write the following as a power series starting at n equals 0. So a couple things to note here is it does want us to turn out a power series, which by the way implies that we need to have an infinite series. We need infinity terms represented here. There are a couple ways to do this, but we'll get there. And then second, we've got a bunch of different little pieces for us to look at as we generate this thing. Obviously, we've got signs to consider, we've got denominators, we've got powers. There's no coefficients in the front other than minus and plus ones, but we'll have to consider those as well. So what I'm going to do here is first and foremost, I'm going to be prepared. If I'm going to write this as a power series, it would behoove me to write out the sigma notation first. And we're starting at n equals 0, so I'm going to go from n equals 0 up to infinity. Now it's just up to me to generate and figure out what is the general term. Like what's describing the pattern here, so that way I can represent it nicely. So let's look at a couple different things. Let's start with the power. Let's look at the power. I've got the power. Power Rangers, lots of things come to mind. Okay, so power. We have 2, 5, 8, 11. So 2, 5, 8, 11. So let's use some of those old sequence skills that we developed in the previous unit. Like, what are we doing to go from 2 to 5, 5 to 8, 8 to 11? I feel like we're adding 3. This looks like, in fact, it's an arithmetic pattern. So what I'm thinking is that this is going to be 3n, and then we got to be careful here. We're used to starting at n equals 1 with sequences, but remember here we're starting specifically at n equals 0. So in this case, I think it needs to be 3n plus 2 as our power. So that looks like a fair thing. Let's see, if we plug in 0 here, n equals 0, that'd be 2. N equals 1 here, that'd be 3 plus 2 is 5. Yeah, it looks like we did a good job. The next thing we're going to look at is let's look at the signs. Also a horror movie by M. Night Shyamalan that really scared my younger brother when it came out in theaters. Or when that alien walks to the birthday party. I enjoy that movie. So in any event, these signs here, we've got plus, we got minus, plus, then minus, then plus. Looks like a traditionally alternating pattern. In this case, though, since we start at n equals 0, that means we want the first one to be positive 1. So I'm going to start to write out my toggle. If I put negative 1 to the n down, negative 1 to the 0 is going to be equal to positive 1, which would fit the first term that we were looking for. So I feel good about this one as well. In fact, I missed a check mark right there, so there we go. That looks like I think we've got that one too. Last but not least, let's go with, trying to pick a color here. Let's go with this plum color. So we'll look at the denominator. So in our denominator, we have root 5, root 6, root 7, root 8. Now, interestingly enough, this is not an arithmetic pattern. It's not a geometric pattern. In fact, it doesn't fit any of those descriptions. It's an either. But the interesting thing is if you ignore the square root for a second, you'll notice that underneath we do in fact have an arithmetic pattern. We're going 5, 6, 7, 8. So in my thought here is I just want to think about first, how do I get 5, 6, 7, 8? Well, we're going to need obviously to go up by 1 every time and start at 5 when n equals 0. So I'm thinking the pattern should indeed be square root of n plus 5. And looking at this, if this is 0, 1, 2, 3, if we plug in 3, we'd get square root of 3 plus 5. That's 8. I think we did it. Where does that leave us? Well, all we need to do is finish out the power series. So in here, I'm going to make a big show of letting this thing look really nicely. So of course, in our numerator, we do have the x. We found that the pattern is going to be 3n plus 2. And then we saw that the sign, which I'm going to put in the numerator just for simplicity, is going to be negative 1 to the n. So there's our toggle specifically to get plus minus when we start at 0. Last but not least, we got the denominator. Oops, I want that radical to look great. There it is. We'll have n plus 5 down below. And that is a perfect way to write our power series out. So there it is. We transformed those first 4 terms by figuring out their pattern. We were able to generate the full power series that represents this entire thing. Now don't get too excited. This doesn't actually represent some sort of simple function that you're like, oh man, there's natural log now. I just made it up so we could look at some patterns and I could talk about some interesting stuff. But at the same time, it's a very nice skill to develop. In fact, I'd go so far as to say this skill is important enough that I do want you to try it and work through it just a little bit. So this is try it number 1. I should probably put that in there. Try it number 1. There are 3 in this lesson. Oops, I put number 3. Try it number 1. So in this case, your job is twofold. You have 2 things to hit. The first thing you're asked to do here is to write the first 4 non-zero terms of the power series given by this particular power series. So you're writing the first 4 terms, so this is the generating question. And the second one asks you to kind of do what we did in the last example. Take a power series with a couple terms given and turn it into a power series. As a heads up, the instructions here are a little more precise than that last example was. It says in summation form. That means you want your result to have a sigma. And it also says it begins at 0, so we want it to be a sigma notation that looks like that. Your job will be to fill in whatever goes in there. So having said that, as I've done with the previous lessons and lectures, I'm going to take a break for a few minutes. It won't feel like a few minutes to you. It'll just kind of pick up in just a second. But I'd highly encourage you to work through this, try it, and then check the answers either in the Google Drive, if you have access to that, which obviously all of you will that's watching it now, or you check on the links once I figure out how to set that system up. So there it is. There's your first try. We'll come back and in a few minutes we'll start to work on manipulating power series. Okay, so we're about to jump in to the next section of the lesson. Obviously, that's how I use the try-its to kind of break things up. Having said that, before I turn the page, let me just kind of point out what it is that's about to happen. So you're not going to see it. You're not going to see it hit you. Okay, so the question you should be asking yourself now after doing this try-it and kind of seeing where we start is like, okay, well, that's all well and good, but what's really the value of power series? Like, why are power series such a useful thing? Like, why is it that I would claim myself that this is one of my favorite things to do? And the answer is it's because it smooths the process through which we can generate Taylor and Maclaurin polynomials. Yeah, we're calling those things kind of series at this point, but the same idea. We'll be able to generate those things really easily because there are properties that, it's the best way to describe this, there are properties that polynomials have that series don't, that will allow us to simplify things, and there's just an organization and cleanliness that series have that polynomials don't. So by combining and kind of bridging, maybe even merging those two together, we're going to get something that's really, really helpful at making the task of constructing Taylor and Maclaurin polynomials easier. So let me show you what I mean. So, and you're not going to this is going to look like a lot at first, be careful. Okay, so on this next page, what we're going to do is we're going to try to write P sub 4 of x, which is going to be the Taylor or Maclaurin series or polynomial, however you want to call it, centered at x equals 0, for f of x equals e to the x squared. Now, I will shrink this in a second, but for the moment, let me expand this quite as much as I can and point out that what you would need to do if you were trying to accomplish this yesterday or in the previous lesson, in other words, trying to describe the fourth degree Taylor, or in this case Maclaurin, polynomial for e to the x squared, your job would be to differentiate that function all the way down to the fourth derivative. Now, the first derivative is pretty easy. You're doing e to the x squared. That's just chain rule. But the problem is, as soon as you've done that once, then suddenly you have a product rule chain rule. Then you have to do the product rule and chain rule multiple times. By the time you get to the fourth derivative, you end up with this massive, what is that, 1, 2, 3, 4, 5, 6 term thing. I didn't even get all of it. You get a 6-term expression out of that by doing product rule and chain rule and all sorts of different rules. It's just really complicated and time consuming. Obviously it works, like don't get me wrong, you're definitely capable of doing this. I mean, it's easy to make mistakes, but you're definitely able to do it. But the problem is, why would you want to? That's a lot of work to generate something that may or may not have a ton of value to us. I mean, just look at that answer. That's such a clean, simple looking answer. 1 plus x squared plus 1/2 x to the fourth. If I saw that, my thought would be there has to be a better, quicker, and more streamlined way to get there. And the answer is that there is. And it's because of our ability to work with these things as either series or polynomials, kind of the synthesis of both. So let me show you what it is that we're going to do here instead. Let me make sure that I use my appropriate way. Okay, so here's what I'm going to do first. I'm going to try to show you and demonstrate what it is that this new kind of perspective is going to offer us. In order to do that, something that I need first is I need to make sure that we know what the power series or polynomial expression is for e to the x. So fortunately for me, we already talked about that in this lesson. So I'm going to go copy this, and I'm going to bring it back in. So here is e to the x. This is the expression for e to the x. Remember, we said it has all the powers, and they're all positive. So it's, what do you call it? It's 1 plus x, or 1 over 1 factorial times x to the first, 1 over 2 factorial times x to the second, etc. So basically, this is where we stood before, and this is where we're going to begin our attack. So what I'm going to do here is I'm going to make an adjustment. And it's a really small thing, but I think this will help a little bit. I'm going to transform this from being a function of x to being a function of t. It's not because I'm a fan of Steven Spielberg alien movies from the 80s, E.T., but it's just going to allow us to plug in a little easier and to let me show you what it is we're about to do. So as I said, I'm going to replace all the x's with t. I'll even put it in a slightly different color so that we can see it. E to the t is 1 plus t plus 1 over 2 factorial times t squared, 1 over 3 factorial t to the third. You get the idea. Voila. Okay, so there's our expression. Obviously nothing changed. I just changed the variable for a moment. The reason I did that is actually a very small one, but a significant one. If we want to talk about the function e to the x squared, that's going to be the same thing. Bear with me. It's going to be the same thing as taking e to the t power and then evaluating that expression at t equals x squared. In fact, I'll even use red. I'll make this even a little better. So what I'm doing here is I'm pointing out that if we wanted to think about e to the x squared and connect it to e to the x, that would be just simply by plugging in x squared for all of those t's. So in fact, you could even take this exact expression that we have here. We could do the exact same thing. You could say that this whole thing is equal to that polynomial evaluated at t equals x squared. And I'm probably getting close to my own image, so let's just shrink that down a little bit. Okay, so we're going to plug in, basically. What am I saying? We're going to plug in x squared here. We're just going to shove it into the e to the x function, and then that should give us what we're looking for. And in fact, just for the sake of spacing, I'm going to shrink all this chain rule work and give myself a little bit more sandbox here. Okay, so here we go. So we want to take that expression we had before and we want to plug in a bunch of x squareds into it. So keeping all this in mind, we're going to write e to the x squared. We're going to plug in x squareds here. I'm going to try to do this with color as much as possible so it's really visible. According to this, we're going to have 1. Then we're going to have plus t. Well, where that t was, we're going to plug in x squared in a little bit, so I'll leave some space for that. Then we'll have plus 1 over 2 factorial times t squared plus 1 over 3 factorial times t cubed plus 1 over 4 factorial times t to the 4th. And although we won't need it for this particular problem because we're only asked for p sub 4, I just want to have some p sub mind. So I just want to have that peace of mind. So I'm just going to leave the general one over here as well. So I'll just write it this way for the moment. Okay. Now, as we said, we're going to plug in x squared everywhere there was a t before. So that's going to put an x squared in here, 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 and an x squared in here. So there is our full, we'll call it the full polynomial or the full power series written out. So now for us, all we want to do is wrap this thing up and write it in as clean a method as possible. So in this case, if we plug in and simplify and clean up what's here, we get that e to the x is equal to 1 plus x squared, plus it looks like 1 over 2 x to the 4th, plus 1 over 6 x to the 6th, plus 1 over 24, of course I'm evaluating the factorials right now, x to the 8th, and then plus dot dot dot. It looks like 1 over n factorial times x to the 2n power. Now, having done all that, that is not answered the question. We've done a little too much work at this point, but notice that we were very easily able to generate the polynomial. We're right here. Our question, though, at the very beginning asked us, let's use green in this case, asked us to write p sub 4. Well, there's p sub 4. For us, p sub 4 would be the 4th degree one. So looking at that green line, it looks like p sub 4 of x is going to be 1 plus x squared plus 1/2 x to the 4th. And again, although I, as always, kind of took a long time, that was a terrible box. Even though I took a little bit of time to develop the idea of what was happening there, hopefully you can see how computationally simple it is. All we had to do here was plug in x squared for x, or t, however you want to think about it, in our already known expression for the Taylor polynomial. Likewise, although we didn't make a big deal about it here, the truth is we also could have just generated this same thing the same way. We could have thought of this as just a sum. It's going to be really tight. I need to shrink it. Sorry. We could think of this entire thing as just a series. There we go. We could think of this whole thing as a series from n equals 0 to infinity. And we could have just taken the expression for e to the x, 1 over n factorial times x to the n, and we could have plugged in x squared in there too, and then just generated the first few terms from that. Like, there's lots of approaches to get there. The important thing is, what we don't have to do is do this massive differentiation, chain rule, product rule, grindy, annoying problem because we have a way that we can get there. We just have to manipulate what we already know and take advantage of the fact that with polynomials, you can plug in expressions like x squared, and you just get the new result that you're looking for. So it comes out just a little bit faster. Now, I don't expect that probably convinces you. I don't think that was necessarily a convincing first demonstration. So let's see what else we can possibly do here and try to see if we can convince you that this is valuable. Or actually, let me just demonstrate this technique again, but in more quick real time. So here's a true, authentic example. So in this one, it asks us to write the first three non-zero terms and the general term, it's important, of the Maclaurin polynomial for h of x equals sine of x to the fourth. So we now want to do kind of the same thing, but this time for sine of x to the fourth. So to kick things off, we begin by writing out what we know the expression is for sine of x. And in this case, since we're looking for three non-zero terms, I'm going to actually just, instead of writing the full, well, let's do it this way. What do we know about sine? Sine is all the odds and they alternate. So this is x minus 1 over 3 factorial x to the third plus 1 over 5 factorial times x to the fifth minus 1 over 7 factorial x to the seventh. And then, of course, plus, and that general term is negative 1 to the n because it starts positive, x to the 2n plus 1 to make sure it's odd, and then over 2n plus 1 factorial. So there is the full sine expression. So starting there. The next thing I want to do, though, is I want to write this for sine of x to the fourth. So what I'm going to do is I'm going to kind of open it up, and instead of having x's in here, I'm going to make room to put in whatever we're plugging in, whatever we're substituting. So this will be x minus 1 over 6 x to the third. By the way, I'm just not going to write 3 factorial. I just like writing the number myself. Then plus 1 over 5 factorial. That's 1 over 120 x to the fifth. And then I'm not going to worry about the seventh degree because we're only looking for 3 non-zero terms. Then last but not least, I'll have negative 1 to the n. And then instead of x to the 2n plus 1, we'll have room for that, 2n plus 1, all over 2n plus 1 factorial. So there's our stuff. Now, of course, what we were interested in, though, was specifically sine of x to the fourth. So that means we need to substitute in that monomial x to the fourth. So that'll be x to the fourth, 1/6 x to the fourth to the third, 1/120th of x to the fourth to the fifth, and then that whole general term, negative 1 to the n, x to the fourth to the 2n plus 1 over 2n plus 1 factorial. And having done all that, the last step that we have is just writing out the expression we were looking for. So for this particular one, our expression is going to be x to the fourth minus 1/6, looks like x to the 12th. You can tell the exponent rules do actually matter here. I'll have 1 over 1/20th, x to the 20th. Got a little small, let me rewrite that. And then from there, we also have the general term, which is going to be negative 1 to the n. When we raise that to the power, it looks like we're going to get x to the, it's going to be 8n plus 4. So now, interestingly enough, looking at those patterns, notice that, in fact, to go from 4 to 8, we add 8, or 4 to 12, we add 8, and 12 to 20, we add 8. So it does look like it's right. And our denominator, though, we just stick with 2n plus 1 factorial. And there would be our expression for sine of x to the fourth. So this, again, accomplishes a problem that I can't convince you because, of course, I really don't want to have to do the chain rule and product rule differentiation over and over again myself. So I can't convince you by showing you how bad it would be. But just imagine if you were going to do this. Think about, oh, actually I can. If you wanted 3 non-zero terms, in order to get up there, look at the degree. You'd have to go up to the 20th derivative. Can you imagine doing 20 levels of product rule, chain, product chain, product, chain, product, chain? Can you imagine that? That'd be miserable. This is easy to work with and fast and clean and very efficient. So this is what our goal is, to actually work our way through. So we've accomplished what we wanted to. There it is. We found our stuff. Before I go on and talk about another property that's out there, let me just point something out for you, because I know as a AP test reader, or someone that grades the test, I know that there are a lot of different ways you can write your final answer. If you desired, you could write this answer in this way. Of course, you wouldn't actually have to simplify any of these pieces, but just as a kind of note for you. If you wanted to, you could also write it this way, and then you could put something for the general term. You could just write it sitting there. I'm not as big a fan of this notation, simply because I feel like it doesn't communicate the knowledge of the connection to that function, but at the same time, it's worth seeing one time. You could do that. You could call this the general term. You could say like GT equals if you want to. Although I hear GT, I think of Georgia Tech, but whatever. So this would be a perfectly acceptable answer as well. So just kind of keep in mind, depending on how you want to write it, like you've got a couple different options. If you want to be a minimalist, there's ways to do it. If you want to be a little more communicative and really emphasize that connection to the function, go for it too. So there is our first full example of showing you that substitution property. Having said that, substitution is not the only advantage that we can subtly get from all of this work. So to kind of follow the same work that we did before, I have a second property for you, which once again is going to save us a bunch of time. And just like I did on the previous one, I'm going to go ahead and make it as large as I possibly can here for a second. So in this case, what we want to do is we want to generate the fourth degree polynomial centered at 0. So it's going to be a Maclaurin, or you can think of it as the Maclaurin series, a finite version though. And we're going to generate it for x times sine of x. So in this case, this would require product rule. And then the next step requires product rule. And the next one requires product rule. And you just keep needing more and more product rule. It's not necessarily difficult like the last one. I'd say the last one was miserable. This one, though, is just kind of annoying. It's just not a fun use of your time. They're easy derivatives, but you just have to keep doing it. And every time you differentiate another level, you run the risk of making a sign mistake, or accidentally switching a sine and a cosine somewhere, or miscounting how many are there and messing up a coefficient. So instead, I want to point out that this is another thing that we can do really, really easily if we just know some stuff. So what I'm going to do, just like before, is I'm going to shrink this down a little bit. And then we're not going to even settle for answering just plain old p sub 4 like we have up there. We're going to attempt to actually answer and find p sub 6, which would be a lot of terms to have to differentiate. We'd need to go to the sixth order derivative if we were doing this the old-fashioned way. But we're not going to, so we should be able to take advantage. Now for this, in order for us to proceed, it would help to begin by knowing what sine of x is, power series is, or what its Maclaurin polynomial looks like. So keep in mind sine of x is the odd one. We have x minus 1/6 x to the third. I think we just did this one, didn't we? Plus 1/120th. Actually, I'll write this with the power, or with the factorials. I apologize. We're not deep enough into this that I should do that. 5 factorial x to the 5th minus 1/7 factorial x to the 7th, and then dot dot dots. The general term, just like we saw before, it needs a toggle so it can alternate. It's going to be x to the odd powers, and then all over the odd factorials. Of course, I say odd factorials makes you think of Fairly Odd Parents, and then I think of TV shows that I would love to watch, I guess. I think those are coming to Netflix or something at some point. I don't remember. I feel like I remember reading that. Who knows? So in any way, things we can control and that I know, there is sine of x. So having said that, since this is sine of x, we want to talk about x times sine of x, in which case the only real change here is that we've suddenly got that x there in front. The cool thing is, having that x in front doesn't actually pose much of a challenge. If we think about it, if we're going to, let's see, oh dang it, no, I was just trying to make this really easy on myself. Okay, hold on, there we go. Okay, so if we think about it, look at it this way. If we want to multiply x times sine of x, since the blue thing over here is just sine of x written as a power series or a polynomial, we can just do the same thing. It's just two representations of sine, so let's just multiply x by that entire thing. Because theoretically, if those two were true, if this is a true equality, oh, that's a terrible underline, but if this is a true equality, then multiplying by x on either side should get us x times sine of x, just in different notations and expressions. And that is indeed exactly what we can do. I believe it's called the product property. You can imagine what we'd do is we'd multiply that x times every single one of these infinite terms. Now be grateful, we don't actually have to multiply by those infinite number, but here it's easy to do. We have x squared minus 1/6 x to the 4th plus 1/120th x to the 6th, And of course, we didn't have to continue, but again, I'm going to be a good soldier and I'll wrap this thing up. The one thing we do need, though, is the general term. And in this case, if we multiply by x, that's just like multiplying times x to the first. Right there, it's not a prime, that's a 1. And if we multiply x to a power times x to a power, we add those exponents. And that's the same thing as having x to the 2n plus 2 divided by 2n plus 1 factorial. So there is our full expression. This is indeed the power series for x times sine of x. But more importantly, all we wanted at the very end of this thing was we wanted to know what p sub 6 was equal to. So in other words, the sixth Maclaurin of this guy. P sub 6 is going to be x squared minus 1/6 x to the 4th plus 1/120th x to the 6th. And there it is. So we found our answer, and once again, all we had to do in this case was the distributive property. We didn't have to do a single product rule. There was, other than knowing the series, like there's not really even that much calculus in there. It's just kind of algebra. But once again, the power of this algebra is that it's allowing us to do something that would otherwise just kind of be painstaking and grindy and just annoying. It eliminates a bunch of stuff and just kind of smooths out the entire process. And you know, as I think about it here, why do I enjoy this so much? It's because I definitely don't remember this process from when I learned it the first time. And this is a lot faster than my old way of doing things, which was just like brute force every time. Just like, I know how to do this the long way, I'm going to do it the long way. I was terrible at mathletes myself in high school because I was like, oh, 11th degree division? Let me just do it that way. Didn't care about shortcuts. But anyway, here's our work. Once again, we now have another property. From here, this kind of brings together a bunch of properties. I've been calling them properties this whole time too. So it's worth kind of pointing out that these properties would likely be something that you could add to your notes if you're recording notes as you go. I think you probably should, but it's up to you. It's your call, your life, your hand, like you be you. But in any event, there's all of our stuff that we're working through. So these are the properties. You'll notice that it begins by defining these power series or these functions f and g as power series. Like once you've got that, then it allows you to do some stuff. So giving these things proper names, let me do that. I want to make sure I use the same terminology as I have in previous years. So in this case, our names of our properties are going to be the scalar property. That first one is our scalar property. Our second one is going to be our substitution property. Oops, sorry. Now we've seen demonstrated, I believe, the substitution property first. That was like e to the x squared. So when we plugged in x squared, we're able to work it through. And again, it's kind of complicated if you try to prove this using Taylor polynomials. But the nice thing is, the one thing you can do is you can see it really nicely as a product of polynomial properties. You can just plug in a monomial to a polynomial and you get a new polynomial. The next one, I don't know why that's written in a different color. That's kind of strange, but that's okay. So that third property is going to be the product property. That was the same one that we just used on the previous problem with x times sine of x, meaning you can multiply monomials through times everything. Works out really nicely. And then the last one, we didn't use it yet. It'll come up in a few days or in a few lessons from here when we talk about the geometric power series, but that's the sum and difference property. So same as we've had previous ones, you're able to add and subtract series the exact same way. So having said that, not the biggest idea in the world, but definitely something that's kind of neat to think about. Like these properties allow us to construct more complicated functions, Taylor and Maclaurin polynomials, which is a huge thing for us because we're going to want to use those to do some estimates. We'll want to generate some for functions that, as I kind of alluded to and what I want to name dropped earlier, the idea that we might be able to come up with a function's antiderivative that we couldn't otherwise. There's lots of really neat stuff that we're able to get here. So again, as it says at the bottom, we can use these to make quick work of complicated functions, Taylor polynomials. We don't have to do that massive differentiation again. That first day is just so that way you develop an understanding of where it comes from. Then once we've got a sense of patterns, we go and attack from there. Having said that, I do want you to try this yourself, but before I get there, I just want to kind of bring the properties together one more time and let you kind of see it all in action once. And as I said, I enjoy doing these problems, so it feels like a useful thing for me to do. I want to work this out for you. So we're going to try to, let's see, the instructions say write the first 4 non-zero terms and the general term of the Maclaurin polynomial for g of x equals x squared times e to the 2x cubed. To kick things off, I need to begin by reminding myself what e to the x's Maclaurin polynomial looks like. And that's one of our big three that we should have memorized, or we should commit to memory if we haven't already. E to the x was the all powers and all are positive. So that's 1 plus x plus 1/2 x squared plus 1 over 3 factorial x to the third plus dot dot dot. And its general term is 1 over n factorial times x to the n power. So there is our Maclaurin for e to the x, one of those big three special functions. So having started there, the first place I'm going to go here is I'm going to focus on one portion of this function. I'm going to focus on the e to the 2x cubed part. I'm going to focus on the substitution half. It's the more complicated part. It's the one that requires a little more effort. So I'm going to make that my focus first. So to kick things off, I want to rewrite this as e to the stuff. And again, as you get more comfortable with it, you can probably do these steps as you go. I'm just trying to be really demonstrative here as I work through. So it'll be 1 plus x plus 1/2 x squared plus 1/6 x cubed plus some other terms that we're not seeing plus 1 over n factorial times x to the n, and then it goes on. Okay, so having said that, we're plugging in not just x to some power this time, but plugging in 2x to the third. So that means each of these terms needs to have 2x cubed plugged in, and that needs to be factored into the entire expression. So we're going to get 2x cubed. So now having done that, let's combine those two together. That's going to give us 1 plus 2x cubed. That first two terms are pretty easy to work with. On this next one, we'll have 1/2 times 4x to the 6th. So we'll have to simplify it. We can do that. Plus 1/6 times 2 to the third is 8x to the 9th. And then plus dot dot dot. In our general term, we'll have 1 over n factorial. And then we've got 2 to the nth power. This is usually the first thing people miss. That gives us 2 to the n. Doesn't simplify or anything. It just is 2 to the n. And then x to the 3 times n would be x to the 3n power. So there is our expression. Of course, we can clean this up, and I'm going to, because I'm not one of those people who doesn't like to simplify. That's 2x to the 6th. This would be plus 4/3 x to the 9th. And then, as we said, we'll have plus 2 to the n over n factorial x to the 3n. There it is. Okay, so there's our work. That's only, though, the red portion up there. So that's only done the second part. That gets us, in fact, if I were to write this all in, that would get us, we said e to the 2x cubed. This is now e to the 2x cubed. Having said that, what our last step here has to be is we need to, of course, distribute in the x squared. We've now got to take care of this guy. That's terrible. Let's do this. We need to take care of the x squared, the monomial that's multiplying through on everything. So that's the same thing as multiplying by x squared on both sides. So we'll multiply the, of course, function e to the 2x or x cubed by x squared, but then we'll also multiply x squared and distribute it to all of the terms that are, that's terrible looking, but close enough. So what does that leave us? Well, on the right side, we're going to get x squared plus 2x to the 5th plus 2x to the 8th plus 4/3 x to the 11th. And then finally, the general term. We'll still have 2 to the n over n factorial. But here we'll have x to the 3n times x to the 2nd. So I've kind of done the exponent rules really quickly before. But keep in mind this is the same thing as x to the 3rd times x to the 4th. In which case you add them together to get x to the 7th. So we're doing the same thing. There's just no like terms up there. So instead we just write this as x to the 3n plus 2. And actually, I don't need to actually write another line. There is what we were looking for. Boom. So voila. So there's our work. Again, we made short work of something that otherwise, seeing as we needed to get all the way up to the 11th degree, would have required 11 steps of differentiation if we'd done it the long way. So again, this is by far the most practical method of doing it. I can't say it's the only way, because differentiating the old-fashioned way would absolutely get there, but it is by far the fastest. Now, having said that, just so that you can see it, just because all this time I've been doing this, I haven't been confirming that anything actually works. I could just be completely hoodwinking you and pretending that all this works. But I want to show you that there is a place if you're ever curious and you want to check if you've done the right Taylor polynomial series, power, whatever you want to think about it as. You can go to a website, which is wolframalpha.com. Of course, we could also go to Desmos and see if it actually converges really nicely. But we want to write here Maclaurin series for, and I believe it was x squared times e to the 2x to the third power. Let's see what it tells us. Oh, it only shows C more terms. Okay, so it says the first 4 terms are, let's try to see if we do this right. Oh, I gotta move this up, sorry. There it is. First 4 terms are x squared plus 2x to the 5th plus 2x to the 8th plus 4/3 x to the 11th. And then, let's see, does it have a general term? It goes 2 to the x squared times, yeah, they didn't multiply it all through. Interesting. But if you multiply it all through, we'll get the same answer. 2 to the k is like 2 to the n, x to the 3n over n factorial, and then we've got that x squared that distributes in. So it looks like we did indeed get it correct and do it correctly. So, cool stuff. So there's the technique itself. Again, I'm not sure if this is being included on the 2020 AP exam. I think this is the end of what's included on there. But regardless, like, this is a huge skill, a hugely important skill to get out of the series stuff. So it's definitely something I want to give you some time to process and practice with. So as with before, I've written out 2 try-its. Again, these aren't just like the previous one. These aren't really easy ones to generate Google form style entry for. So these are ones where I'll definitely recommend take some time, work through these. Like, that's the one advantage you have of not being in a traditional classroom. There's no bell that's going to ring on us here. So take your time, work through, check your answers with the solutions that are posted or possibly even linked in the description. I don't think they're there yet, but they will be eventually. And make sure you've got this down so that way you're in good position going forward and working through things. So this isn't the end of the lecture. This is just kind of our final stopping point or our pausing point, but the next section moves really fast and is just kind of an extra little like, hey, cool, look at this kind of thing that we would want to get to. So take a few moments, work through the try-its, and then we'll be right back and try to continue and wrap up this lesson. Okay. As I said, I've got one last little section. It's another set of like little operations to kind of show you. This opens up a really powerful world though, so let's jump into this last portion of this lesson. I will say before I click the button though, I apologize in advance. This lesson does tend to be one of the longest of the year, simply because there's lots of little things, there's lots of pieces to tie, and there's lots of examples to try to demonstrate it for you. So basically just keep in mind this is as long as it gets. This is just one of those like extended ones. Okay, so as it says at the top, there's 2 more operations we can do with Power Series that are, quote, pretty cool. And it says it in writing in ink on the screen, so you know it's true. So these last 2 operations are ones that you didn't know until you entered calculus for the first time. So truthfully, the operations we're going to look at are differentiation and anti-differentiation. And I submit that you're actually going to be able to work with these really, really easily and cleanly in just a bit. So what I wanted to do here, and this was a kind of a change from what I was planning. I know you can't see the clock, but I took a little bit extra time to kind of reset this up. Basically, I want to demonstrate for you first differentiation. So I'm going to basically take the derivative with respect to x of the power series for sine of x. Now when I do that, something kind of interesting to think about is that means that I'm really differentiating all of these different expressions. And each one kind of has its own approach. So I'll just do one at a time. I'll start with the center one, the one that's differentiating the term-by-term version of this power series. So if I take the derivative of each term, these aren't very difficult to work through. We're going to have 1, and then for the next one, we'll have 1 over 3 factorial times 3x squared. Then we'll have plus 1 over 5 factorial times 5x to the 4th. And then minus 1 over 7 factorial times 7x to the 6th. And then of course we still have a general term. Now keep in mind the only thing we're differentiating here, since we're differentiating with respect to x on this expression, is the portion that has an x, which means that our last general term is going to maintain the negative 1 to the n, and it's going to maintain the 2n plus 1 factorial. But on the other portion, we're going to bring down the power and then multiply by x to the power minus 1. So now, having done all this, let me point out that if we simplify and clean some things up, some interesting stuff is going to happen here. Take a look specifically at this. If we have 3 factorial and 3 over 3 factorial, that'll leave us with of just 1 over 2 factorial. The 5 and the 5 factorial will leave us 4 factorial. The 7 and the 7 factorial will leave us 6 factorial. And in fact, even here, kind of cool to note, since 2n plus 1 factorial is the same thing as 2n plus 1 times 2n factorial, the 2n plus 1's divide out. And what we're left with on this side is going to be 1 minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth, and then our general term. Can you see the smile starting on my face? I just find this so cool. Get negative 1 to the n times x to the 2n divided by 2n factorial. Out of curiosity, have you ever seen that series or polynomial or expression before? I think that you probably have. And in fact, I bet you already have recognized what it was. Let's ask ourselves here, even though we were thinking about it as differentiating a power series, what's the derivative of sine of x? Cosine of x. So when we differentiate the power series for sine of x, we end up with literally the derivative of sine of x's power series as well. And in this case, because the derivative of sine is cosine, we're left with the power series for cosine. So in other words, we see in just another way to confirm that that derivative of sine is equal to cosine. Likewise, just to kind of note it out there, just because I think it's probably good to see this once as well, if you differentiate a summation, once again, the only thing that's being differentiated is, colors matching the same way. The only thing being differentiated is the part that has the x. So just like we did on the general term over here, what that leaves us with is the sum from 0 to infinity of negative 1 to the n over 2n plus 1 factorial. And then the other portion becomes, just like we saw, 2n plus 1 times x to the 2n. And just as it did before, we can divide that out. It'll leave us with 2n factorial, and we'll end up with the sum, expressing, of course, the exact same thing that we just saw in the other versions. So in other words, powerful stuff. We actually end up with the derivative as cosine, just like it was before. So this is just kind of it's not a proof at all. It's not a formal proof. It's just kind of a neat little demonstration that, hey, differentiation does exactly what you expect it to do, no matter how you differentiate it either. If you decide you want to differentiate the summation version, the power series written in sigma notation, then that's great. You can generate the terms. If you want to go term by term and differentiate that way, you'll get the terms the same way. And all of those things match the derivative rules that we already knew just the same. So it's just kind of a really neat piece, a really neat outcome for us to end up with. Having said that, in addition, or maybe even more powerfully, there's something more we can do. And the truth is, the more is probably valuable because I think you knew before this problem that the derivative of sine was cosine. Here's the more powerful thing. You can also anti-differentiate. You can perform quote-unquote integration if you'd like to. Here's the thing though. If I give you some problem, if I give you certain problems, they're easy. If I give you the integral of cosine of x, you'll know the answer is sine of x plus c. But here, notice that what I've given you is the sine of x cubed. And just, let's throw Wolfram Alpha back out there for a second. What is the integral of sine of x cubed? Let's see. Oh, shoot, this thing's fighting me. Excuse me. Integral of sine of x cubed. Let's see. What does this beautiful expression equal? Yeah, that doesn't look so good. This is showing us that there's not a closed form expression for this. We don't have it. This is non-antidifferentiable. We can't come up with a closed form expression. All we can do is write a function from 0 to x of sine of t cubed or something. So instead, let me point this out. We can actually do this problem and figure out a representation, and actually we can find an expression for the entire function that has this derivative if we use the powers and properties of power series. The powerful properties of power series, I think what I want to say. So let's start with something we know. We know sine of x, and in this case I'm only going to worry about a couple terms. Sine of x is x minus 1/6 x cubed plus 1 over 5 factorial, so that's 1/120th x to the 5th, and its general term, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. So actually this is exactly the same expression we had before, I'm realizing right now. So there it is. Okay, so what do we do? How do we kick this off? Well, first and foremost, if we know sine, we should be able to figure out sine of x cubed really easily. And I'll do this one more authentically timed. I'm going to plug in x cubed everywhere where there's an x here. So here it's not kind of the perfect notation, but it's kind of like I'm plugging it in right there. Typically I don't show this step, I just kind of do it. So again, feel free to follow suit if you feel comfortable. This will be x to the 3rd minus 1/6 x to the 9th plus, it looks like 1/120th of x to the 15th minus some other terms, and then eventually we get to our general term, negative 1 to the n, x to the, I think it'll be 6n plus 3 if we use the exponent properties, over 2n plus 1 factorial. And then I did notice that n just kind of had a problem. So there it is. So that is sine of x cubed. So now what is it that we're going to do from here? Well, let's think about it. Let's match this operation. We want to anti-differentiate this, so we should be able to do that. Let's pull it over here. I'm trying to give myself a little bit of room here. There we go. Okay, so what am I going to do? I'm going to go ahead and just set this thing up. I'm going to take the integral with respect to x, or anti-differentiate this function, which should be the same thing as the integral of this thing, dx. When I do, I can go term by term, of course. This will be 1/4 x to the 4th. This will be 1 over 6 times 10, so 1/6 times 1/10 x to the 10th, so 1/60th x to the 10th. The next one is going to be, 1 over 120 times 16. I'm just going to put 120 times 16. Yes, I'm going to be one of those people as well. X to the 16th. And then from here, we'll do the same thing with this next term. Be careful though. What we're really having to work through is the part that's not a scalar, which is the x to the 6n plus 3. So as far as coefficients, that part's going to stay because there's no x in there. And then we'll have the 2n plus 1 factorial that will stay. But the other factor we're going to get is when we add 1 to the power here to use the anti-power rule, we'll get 6n plus 4. And then we'll need that 6n plus 4 as a factor in the denominator as well. And then of course we can go ... This is going to be equal to the integral of sine of x cubed, something that we can't actually represent any other way. So again, that's one of the neat things about this. Did I not do this correctly? Oh, good. Okay, I was looking at the triad answers. I was going to say, wait, that looks wrong. But in any event, that's just one of the cool other things that we can do. These power series aren't something that work for a very narrow purpose. They're actually really powerful. And in this particular piece, like this little chunk at the end, I think you're really seeing the biggest power of these things. These power series allow us to quickly come up with an expression that represents a function that may or may not be easy to differentiate or anti-differentiate or simply to represent or plug into. And by converting it into a polynomial, we suddenly open up a whole new world. Suddenly we can do things easily like anti-differentiating and differentiating and evaluating to create estimates. We can do all those things because polynomials are easy to work with. They're easy to differentiate. They're easy to anti-differentiate. So our whole goal here is to just open up more possibilities for ourselves and suddenly run into the discovery or suddenly discover that we don't have to worry anymore about difficult expressions. As long as we can transform them and construct their Taylor or Maclaurin polynomial, we have a pathway to do all sorts of powerful things with them and to represent things that as recently as, yesterday would have seemed functionally impossible. Like there's just not even a way. Wolfram Alpha can't solve it because, well, it can't solve it and find something because there's no answer, but I'm not putting down Wolfram Alpha. I love that place. So having said that, that was your demonstration of differentiating and integrating or anti-differentiating using power series as well. Something else you'll be asked to do. So having said that, I'm going to wrap this up with the triad. This is one of the triads that I've kept since the very beginning when I first learned like this stuff and kind of taught this lesson. Is you're just going to be, you're given a power series and then your job is to anti-differentiate and differentiate it, and come up with expressions for each one. So I encourage you to take a look at that. As with the previous two in this lesson, those try-its will have their solutions available somewhere for you. So keep an eye out on either the Google Drive or possibly for links in the description, although I definitely know they won't be there when I first post this video. But in any event, hopefully this lesson today has given you some exposure to kind of the powerful, wondrous world of Power Series, in which case we sort of just kind of bypass all that nitty-gritty calculus-based algebra of differentiating to end up with a bunch of coefficients. This is kind of our new streamlined, fast, efficient, aerodynamic, that sounds like a great word for it. It's a great way for us to work through and develop and find these polynomials, which just open up a bunch of doors for us. True though it is that we're not going to be working through and walking through all of those doors ourselves right now, particularly in the middle of a pandemic. The truth is, these are powerful skills that will pay off in further courses in the future. Heck, I had a friend that was just taking the complex analysis class, and that person's final that I got to see after they were done, because it was all take-home, actually had a bunch of Taylor series, complex Taylor series. They show up in physics, they show up in all sorts of places. So this is one of the greatest skills that you can have there, is this appreciation for the fact that although we think of them as polynomials, the truth is they're really series too. And those series just allow us to do all sorts of interesting things and kind of simplify the process of construction. As with every previous lesson, thank you for watching. I appreciate you taking the time to attempt to learn this material. This is one of those sort of heavy lessons. I think that it's a very light topic, but I think it's heavy just with a lot of thinking and a lot of connecting of topics, especially tough because we're just learning these skills for the first time. So I encourage you to pause at different times, or hopefully you paused at different times or you took your time through it, maybe even separate it out over multiple days. I'll be sure to recommend that when instruction actually begins. But in any event, I hope this has been helpful to you. I hope this has been a good comprehensive coverage with a good number of examples and try-its mixed together. And I hope you're staying safe and healthy and feeling well and finding ways to keep you and your family safe and entertained and comfortable during this time. So as always, thank you for watching and have a great night.